Hey guys, in this video we're going to talk about Chapter 2, Section 3, Piecewise Functions. So before we get into what we're actually learning this week, I want to do a little bit of a review with you guys. So the first thing I want to talk about are inequalities. So we have greater than right here, we have less than, we have greater than or equal to, and finally we have less than or equal to. And I just want to review what these symbols mean. So you can read a statement like this with an inequality from left to right. If you read it from left to right, just like you would, like if you were reading a book, you could read it from left to right. And what you could say is x is greater than 2, right? Because this inequality is opening up towards x. Okay, so x is greater than 2. You could also read it from right to left, starting at 2. And so since the point is facing 2, the way that we say it reading from right to left is 2 is less than x. All right, so since it's pointing towards 2, it means less than. If it's opening, it means greater than. If it was opening towards 2, it'd be 2 is greater than x. Okay, let's look at the next one. So reading from left to right, we could say x is less than 2, right? Because the point is facing x. If we read it from the other way, if we start at 2, well, this time, reading from right to left, the inequality is opening up towards 2. So we would say 2 is greater than x. Both of these things mean the same exact thing equivalently, okay? So the next one is the greater than or equal to sign. So it means that that whatever x is, it could be 2, but it also could be bigger than 2. Okay? And so reading from left to right, you would say x is greater than or equal to 2 because it's opening up towards x. If you read it from right to left, you would say 2 is less than or equal to x because the point is facing the 2. And finally, x is less than or equal to 2. Since the point is facing x, it's x is less than or equal to 2, reading from left to right. Reading from right to left, 2 is greater than or equal to x. Alright, so something else that's important to know is that if we have greater than or equal to or less than or equal to, we used a closed dot. And that's to indicate that whatever number we put the dot on is actually included in our set. We use greater than and less than with an open dot. So we use open dots to represent less than or greater than. Basically, if you put an open dot on a number, you're saying, okay, I'm not including this number in my set. Sometimes these things are called strictly greater than or less than because we don't actually include the number. Alright, so let's do some examples where we graph some sets on a number line using this notation. So we have the first set, x is greater than 1. I want to just make clear here, this is a set. This is actually an infinite set. Of numbers. And it's actually what we call uncountably infinite, meaning, well, we're not going to go into that right now, but the idea is that any number you can think of that's bigger than 1 will be in this set. So like 2 is in the set, 3 is in the set, but not just whole numbers. 2.333333 is in the set. 2.561892 is in the set. 1,000,056.32 is in the set. So any number you can think of is in this set. And we can represent this set on a number line pretty easily. All we do is we take the number that we see, which is 1, and we plot it on the number line. So here's 0, maybe -1 and 1. I'm being kind of sloppy here. But now you look at the symbol. If it's a strictly greater than or less than symbol, you use an open dot. So this is strictly greater than, so I'm going to put an open dot on 1. And to represent every single number bigger than 1, I need to represent it with a shading, and I'm going to shade to the right of 1. Right? All of these numbers are in the set, and I didn't write the numbers because we can't write all of them, but included in the set is 2,652,700.46. Okay, so like this little shading is representing uncountably infinite numbers. Okay, so that's the set. And we put the open dot there because we're saying, hey, I'm not including this number 1 in the set. But everything that's really close to 1, like, for instance, 1.000000003 is in the set, but 1 actually is not in the set. It's pretty cool. All right, let's go ahead and look at the next one. We have x is less than or equal to 3. So I'm just going to I'm just going to be pretty basic about this. I'm just going to put 3 right there because I say so, right? Because a number line is infinite in length. I don't really have to measure where I put my numbers. I could have put 3 right here if I wanted to, but I'm putting 3 there, and I'm putting a closed dot on 3. And the reason is because of this less than or equal to. I'm saying, hey, in this set, I'm actually going to include 3. It says the set consists of all numbers less than or equal to 3. So to indicate less than or equal to, I shade to the left, right? Because everything less than 3 or equal to 3 is included in this set. So in this shaded region, 2 is included, 1 is included, 0 is included, negative 1,673,000 is included. All of those numbers that are less than 3 are included in this set. So that's how you do that. All right, now we have what we call like I don't know, maybe a compound inequality. Basically, you're just going to plot the two numbers. We have negative 1 right here and 2 right here. And you always, you can start, you want to start at the middle thing, right, which is x. And it says, if we read from right to left, this says x is greater than or equal to negative 1, right? If we read from starting at the middle and we read going to the left, x is greater than or equal to negative 1. But then if we look this way, if we just read starting at the middle from left to right, this is x is less than 2. Okay, so we kind of have a sandwich here. We have x is greater than or equal to negative 1. So that represents everything here. X is greater than or equal to negative 1 with a dot right here. And then x is less than 2. We're going to put an open dot at 2 because it's strictly less than. And we're going to shade everything to the left of 2. Right? That's what less than means. And where these guys intersect, where the colors overlap, is what we're actually shading on our picture. So if I were to redraw this, like if I were to redraw the answer, it would be negative 1 to 2. And then where they overlap is this region right here. So I would just shade, and I would put open dot here and a closed dot right here. So this would be my answer. All right, write this as an inequality. All right, so we can say x is our set of numbers, and it's sandwiched between negative 8, and it's bigger than negative 8, right? Because it's shaded to the right. So bigger than negative 8, x is bigger than negative 8, but at the same time, this set of numbers is going to be less than or equal to 6, right? Because of this closed dot right here. So x is sandwiched between negative 8 and positive 6. Alright, so now that we did that little review, we're going to actually talk about what piecewise functions are. So basically, I have a really kind complicated definition, a piecewise function is a function that's made up of different pieces. I'm joking. It's this. I guess this isn't the technical definition, but I like this definition because it makes sense. So we have this piecewise function right here, and it's made of 3 different graphs. So the first graph is right here. It's this line. The second graph is this line right here. And the third graph is this line right here. It's made up of 3 different pieces. And what we're going to look at doing is we're going to look at writing formulas for graphs that look like this. And we're also going to talk about going in the other direction and actually graphing from a piecewise formula. So the first thing you guys need to know is the notation. So use bracket notation. Basically, this is what a piecewise function looks like. You have some curly bracket right here, and then there's certain conditions that make your pieces up. So like this first row is a piece, this second row is a piece. Okay, and so they tell us that there is a piecewise function. It's defined by y equals 2x plus 1 for negative values of x. So what I can do, instead of writing y equals, I already have the y equals right here. I don't need to write the y. I can just write my first piece. The first piece is this line, 2x plus 1, and it tells me, hey, this only applies for certain values of x, specifically negative values of x. So my y is going to be 2x plus 1 for x is negative. How can I write that with an inequality? I can say that x is less than 0. That's what negative numbers mean. Anything less than 0 is a negative number. So that's my first piece. And the second piece says, my second piece is y equals x minus 4 for x values that are greater than or equal to 0. So my second piece is going to be x minus 4. And this is only when x is bigger than or equal to 0. So we have just made a piecewise function right here. And what this is going to allow us to do, it's going to say, you know, sometimes we have different rules for different values of x. That's the basic idea here. Sometimes we have different rules for different values of x. So because of that, you know, we need to choose which rule to use. This rule or this rule? Well, it depends on the situation. It depends on what x is. So let's talk about how we can evaluate these guys. So it says evaluate f of negative 2. Now this is my x value, right? It's my input. And the rule that I'm picking depends on the x. Now look at what rule I use for x is less than 0. I'm going to use this rule. So here I'm going to say, well, I'm just going to plug in negative 2 into my function rule for x. And again, I'm using the top one because my x, which is negative 2, is smaller than 0. Alright, so then I just evaluate negative 4 plus 1 is negative 3, and that's my answer. Now what about f of 0? Do I use the top rule, 2x plus 1, or do I use the bottom rule, x minus 4? Well, we have to go back to our domain on the right side, and we say, well, my x is 0, so is 0 less than 0? Is that true? No, so we don't use the top rule. But the bottom rule says, hey, x can be 0, or it can be bigger than 0. So we have to use this rule right here. And we're just plugging in our x value into this rule. So our x value is 0, so instead of x, we're writing 0 minus 4. And that's going to give us negative 4. Alright, let's do one more like this, f of 6. So 6, where does 6 fall? Does 6 fall in the category of rule number 1 or rule number 2? Well, 6 is a number that is bigger than or equal to 0. So we have to use this rule right here. So I'm just putting 6 in for x. Again, this is x. So instead of x, I'm writing 6 minus 4, and that's going to be 2. So that is how we can evaluate a simple piecewise function like this. Okay, so let's look at this example. So on the left, we have our two rules for the piecewise function. On the right, we have our sort of domain for these set rules. So if it helps you, you can always make a number line for each of these. So like the first one, we have x is between -1, including -1, and +1. That's going to be this region right here. And then for the second one, x is going to fall between 1 and 5, but it's not going to include 1. So we're going to put an open dot there. And then it goes up to 5, and we're going to put a closed dot because he has a less than or equal to, and we'll shade in between. So these are the number lines for each of our rules. Okay, so the first one, we're evaluating g of 0. Remember, we first look at this to determine what rule we need to use. So depending on where 0 falls, does it fall on this number line, or does it fall on this number line? Well, it falls in this shaded region, right? Because 0 is smack dab in the middle of -1 and 1. So we have to use this rule right here. So it says, hey, I'm going to put in 0 anywhere I see an x. So -4 times 0 minus 1 is 0 minus 1 is -1, and that's my answer. What about g of 3? All right, well, first things first, we look at where x falls. Does x fall between -1 and 1? Or does x fall between 1 and 5? Well, x is between 1 and 5, right? X is bigger than 1 but less than or equal to 5, so we use this rule right here. And it says, hey, anywhere I see an x, I'm going to plug in a 3 into that rule. So we have 2 times 3 minus 7. 6 minus 7 is -1. And that's our answer. Alright, so another mini review. We're going to review linear functions. So linear functions are just lines. And I'm going to show you guys a bunch of piecewise functions that are made up of pieces of lines. So we need to remember what linear functions look like. Now, we have two components of a linear function. They are written of the form y equals mx plus b, where m is the slope and b is the y-intercept. So the slope measures the steepness, right? How steep a line is. And the y-intercept is where the line crosses the y-axis. Okay, so if we want to graph y equals 2x plus 1, there's a few different ways to do this, but I think the easiest way is to first start with the y-intercept, which is 1, and put a point right there. And then slope, the slope is 2, or 2 over 1, and remember with slope we do rise over run. So from the y-intercept I can go up 2, 1, 2, so this is the rise part, and then I can run 1 to the right. So I rose 2 and ran 1, and then I plot my other point and just connect the two. This is plus 2 plus 1. Rise 2, run 1. Alright, so we can also find equations of lines if we're given 2 points. So the way that we can do that is to first find the slope. And there's a simple formula for the slope. It's y2 minus y1 all divided by x2 minus x1. And these ones, these x1, y1s, that's a point. So we can say that this is our first point, x1, y1, and this is our second point, x2, y2. Now you can't, you couldn't say this was x1, y2. Like, the ones have to stay with the ones, the twos have to stay with the twos. But you could have said this is x2, y2, and you could have said this is x1, y1. It doesn't matter. But whatever number point you're choosing, you have to stay consistent with those numbers. Okay, so let's find the slope using this formula. Now y2 in our case is 2, so we have 2 minus y1 is 6, all divided by x2, which is 1, minus x1, which is negative 1. Now on the bottom, these double negatives make a positive, so we have 2 minus 6 over 1 plus 1, and then on top we have negative 4 over 2, and that's going to give us negative 2. So that's one piece of the puzzle. We know what our slope is. Our slope is negative 2. And the other piece of the puzzle is to find b, the y-intercept. And to do that, all you have to do is plug in values into our basic form, y equals mx plus b. So we want to plug in something for m, x, y, and we want to solve for b. Now we know what m is. For x and y, we can choose this one to be x is negative 1, y is 6, or we could choose x is 1, y is 2. Either one of those will work because it's a x comma y on the line. Either one works. I'm going to use the second one. Okay, so the second one, x is 2, and y, wait, I'm sorry. The second one, x is 1, actually, because that's the first number in the ordered pair. And y is 2. Okay? And again, you can't go switching around. You can't say, okay, well, x is 1 and y is 6. No, I chose this point right here. So x is 1, y is 2. And m we just found right here. M was negative 2. And so all we have to do is plug in these three things into our basic equation right there, giving us 2 equals negative 2 times 1 plus b. And we're just going to solve for b. On the right side, if I multiply out negative 2 and 1, I get negative 2. So I get 2 equals negative 2 plus b. And then to undo subtraction of 2, I can add 2 to both sides to give me b equals 4. So now I have all the pieces to the puzzle, and my equation is y equals negative 2x plus 4. I just plugged in my m and my newfound b. Let's try another one. So first thing you want to do is find m, and then you want to find b. So m, we have y2 minus y1 over x2 minus x1. I'm just going to say the first point's x1, y1, and the second point is x2, y2. So with that information, we have y2 is 0, minus y1 is 8, over x2 is negative 4, minus x1 is 6. Simplifying the top, we get negative 8. Simplifying the bottom, we get negative 10. Double negatives become a positive when divided. And finally, I can divide top and bottom by 2 to give me a simplified slope of 4 over 5. So we have that piece taken care of. And now we just need to figure out what b is, the y-intercept. And as I said, you know, in order to figure this out, we need an x and a y, a corresponding y. Let's be careful with that. And we can pick either this as our x comma y, or we can pick this as our x comma y. Doesn't matter. I'm going to pick this one. In this case, x is negative 4. That's our x value, and our y is 0. And so we're just plugging everything into our base equation, y equals mx plus b. So y is 0, m is 4 over 5, x is negative 4. We don't know what b is. So if we multiply 4 over 5 times negative 4, that's the same thing as negative 4 over 1, multiply straight across and get negative 16 over 5. So let's rewrite that. 0 equals negative 16 over 5 plus b. And to undo subtraction of 16 over 5, I can add 16 over 5 to both sides to isolate b. And I get my answer of b is equal 0 plus 16 over 5 is just 16 over 5. So that is my answer here. And now that I have m and b, those are the things that I need to make the equation. So let's erase this. So I'm leaving y alone. I'm subbing in my m, which was 4 over 5. I'm leaving x alone, and I'm subbing in my b, which is 16 over 5. This would be my final answer there. Okay, so let's take a look at some examples where we actually have to find a formula for a piecewise function. So we have two pieces. We have this little line segment right here, and we have this little line segment right here. And the goal is to write formulas for both of these line segments in y equals mx plus b form. So, you know, we can use the slope, rise over run, to do this pretty easily in this case. And we can also notice that in this line segment, the y-intercept is actually given for us. So let's go ahead and just write out our basic idea. We have f of x, which is our function. So this is the formula for the function we're going to write. And then we have some curly braces here, and we have piece 1 with some domain, and then piece 2 with some domain. So this is piece 1, and this is piece 2. And I think the easiest thing to do before we start writing equations for the lines is to figure out what the domains are for each piece. And domains is just what x can be, right? So if we look at this first piece, we start the first piece at x equals negative 4, right? This is x equals negative 4. And it goes on until x equals 1, right? This piece goes from x equals negative 4 to x equals positive 1. So that's our domain for the first piece. And how do we say this with inequalities? How can we say that x is between negative 4 and 1? Well, we just put x in the middle, and it's going to be bigger than or equal to negative 4. And at the same time, it's going to be less than or equal to 1. And the little line at the bottom of these inequalities comes from the fact that we have closed dots on both ends there. So that's our domain for that piece. Now what about this piece? Where does x start and end? Well, the lowest value that x takes is x equals 1. And the highest value that x takes is x equals 3. So this thing varies between 1 and 3. And with 3, it's going to be less than or equal to, because we have the closed dot here. And with 1, it's just going to be greater than, strictly greater than, because of the open dot. So we're not actually including that. Alright, so that's the easy part, finding the domain, I think. Now we have to actually figure out what the formulas for the lines are. So, for the first line, we want to put it in y equals mx plus b form. And notice that I have b already. I have 1 for b. And I just need to figure out what is m. Well, I can do this a couple different ways. I can use ordered pairs and use my formula, or I can just do rise over run. So, you know, I can pick 2 points on the segment, so like maybe the endpoints, this guy and this guy, and I can see how much I need to rise and how much I need to run. So I'm rising 1, 2, 3, 4, 5 until I'm level with this point right here. So I'm rising 5, so that's plus 5, and I'm running 1, 2, 3, 4, 5. I'm also running 5 in the positive direction and the positive x direction. So rise over run, we have positive 5 over positive 5 is going to give me a slope of positive 1. So my formula here is just y equals 1x plus 1. Y equals mx plus b. But I don't need to write the y because I already accounted for that with this in the front. So I can just write 1x plus 1. Alright. Now let's go ahead and do the other line. Now this one has a negative slope, because if I put a person on it, he's walking downwards instead of upwards, like this one. Alright, so let's check this one out. So let me go ahead and maybe clear this a little bit. So we're just looking at this guy now, and we're trying to figure out what is the y-intercept and what is the slope. Well, this one, we don't actually have the y-intercept, so we're gonna have to use a point and a slope to figure out what that is, right? Because we don't see where it's going to intersect the y-axis right off the bat. But maybe you guys can see it. Let's go ahead and figure out what the slope is. So to get from this point to this point, I have to rise 1, 2 in the negative direction. So I'm rising, quote unquote, -2. And then I'm running 1, 2 in the positive direction. So since I went to the right, that's positive x. Since I went down when I rose, quote unquote, I attached negative to it. So again, this is rise over run. And so my slope is going to be -2 over +2. -2 divided by a +2 is a -1. So my slope here is -1. And to figure out what the y-intercept is, we can do the trick that we did before. We can pick a point, plug it in, and solve for b. So if I pick this point right here, this point has an x value of 3, right? That's the horizontal component. And how far down is it? Well, it has a vertical component of -3. So this is my x comma y. And you could have used another point on this line segment, it doesn't matter. But the point is that we can plug in y, x, and m into this equation to solve for b. So we have y equals m times x plus b. Let's go ahead and solve for b. On the right side, when I do -1 times 3, that's going to give me a -3 plus b. And now I can add 3 to both sides to get b equals 0. So that is my my y-intercept. And putting these two things together, my rule is going to be y equals -1 x plus 0, but of course we don't have to write the plus 0. So that is the line that's this little segment, line segment right here. And this is my rule. So that's how you can write a formula for a piecewise function. Alright, let's try this one. So again, we're doing the same kind of story here. We have two line segments. We're going to first write the domains out, because I think that's the easiest thing to do. So we have this guy for some x values, and then we have this guy for some x values. So the first thing I like to take care of is the domain part, in the far right. And so I want to see where x varies with both of these. Now, it tells us that the starting point at this purple line is x equals 4. Right? That's this point right here. It says, hey, this is x equals 4. So it starts at x is bigger than or equal to 4 because we move along to the right. So it's bigger than or equal to 4, but at the same time, it's going to be less than or equal to, well, this endpoint is going to be x equals 12, right? So we're varying between 4 and 12. X is bigger than or equal to 4, but it's smaller than or equal to 12. So again, this is x equals 4 right here. This is x equals 12, and we're told that with the first number in our coordinate. So that's where the first domain is. Now what about this this gold line segment? Well, we start at an x value of 20, so x is going to be bigger than or equal to 20, And we end at x equals 32. So it's going to be between 20 and 32. And everybody gets a less than or equal to, greater than equal to, because all we're dealing with here are closed dots. We don't have any open dots to worry about. So now that that's taken care of, let's go ahead and write the formula for the functions. Now, it might not be obvious here to do rise over run because it's just, it might look a little bit clunky. So instead of doing rise over run, because I have like a fractional value right here, or so it seems to be, and you know, you can do rise over run if you think about it. I mean, it's not too bad, because like you're going from y equals 10 to y equals 14. I'm rising 4, and then I'm running in the left direction. I'm going from 12 to 4. So I'm actually subtracting 8 from 12, right, to get to 4. So rise over run, so this is going to be positive 4 over negative 8, and that's going to reduce to, if I divide top and bottom by 4, that's going to be negative 1/2. So my slope here is negative 1/2. You could have also found that by using the formula. So let me just show you how we would do that. We would pick these ordered pairs to be our x1s, y1s, and x2, y2s. So here I have y2 is 10 minus y1 is 14, divided by x2 is 12 minus x1 is 4. On top we get negative 4. On bottom we get 8, and you know the net result is the same. We still get negative 1/2 for our slope. So you can use the formula if you want to. Now we need to figure out what the y-intercept is of this segment. And to do that, we need to choose an x comma y to plug into the basic formula y equals mx plus b. Now, which one you pick doesn't matter to me. I'm going to pick this one right here. I'm going to pick 4 is my x value, and y is the 14 is the corresponding y value. So we have x is 4, y is 14. Again, you could have picked x is 12, y is 10, but I'm just picking this other point. And m is negative 1/2. So plugging in these three things into this basic formula, I get 14 equals negative 1/2 times 4 plus b, and I can solve for b. So on the right side, negative 1/2 times 4 over 1, negative 1/2 times 4 over 1, multiply straight across is negative 4 over 2. Negative 4 divided by 2 is negative 2. So this becomes negative 2 plus b. I can add 2 to both sides to get b by itself, and I get b is equal to 16. So you can define a line with a slope and a y-intercept, and that's what that purple segment is. It's going to be y equals negative 1/2 x plus b, which we just found was 16. So that's the first line segment. Now we need the equation for the other one, and we're going to do the same exact process. Now again, you can just look at the picture and do rise over run, or you can use the formula. It really doesn't matter. You're going to get the same answer. I'm just going to do the picture just to be consistent, I guess. Okay, so rise is y, right? So I start at 4 and I'm rising all the way to get to 28. So what's the difference between the height of 28 and the height of 4? Well, that's going to be 24, right? I rise up 24 units, and it's plus because I'm moving up. And then I start at x equals 20, and I move over to x equals 32, right? I start at x equals 20, I move over to x equals 32, and the difference in that is 12, and I'm increasing by 12 to get from 20 to 32. So my slope, my rise over run, I'm rising 24, and I'm running 12, both in the positive direction because I went up and I went right to get to the next point. And 24 divided by 12 is going to be 2, so that is our slope here for that yellow segment. Now again, to find the y-intercept, we can use that trick. I'm going to pick x equals 20 and y equals 4. You could have picked this one as well. X is 32, y is 28. It doesn't matter. But the idea here is the same. We're going to take the x, the y, and the m and plug it all into y equals mx plus b to solve for b. So we get 4 is equal to 2 times 20 plus b. Solve for b. On the right side, I can simplify 2 times 20 is going to give me 40. And then I can subtract 40 from both sides to get b alone. So I get b is equal to negative 36. All right. So my equation here is going to be y equals m, which we found to be 2, x plus a negative 36, which is just minus 36. All right, so these are my two equations of the lines that we were given, and these are the domains of each line segment, I should say. Okay. So let's look at this one. All right, so we have 1, 2, 3, 4 pieces: a red piece, blue piece, green piece, and yellow piece. I'm gonna have 4 pieces in my piecewise function. Piece 1 with domain 1. Piece 2 with domain 2. Piece 3 with domain 3. And finally, last but not least, piece 4 with domain 4. So I like to get the domains out the way. What can x be? So this red line starts at an x value and ends at an x value. Like the lowest x value we can find for this red line is going to be x equals, let's see. If we count 1, 2, 3, that's negative 3. So it starts at x equals negative 3, so it's going to be strictly greater than negative 3. And the strictly is because of this open circle right here. So it's going to be greater than negative 3. And it's bounded by this x value right here, which is 1. So it's going to be greater than negative 3, but less than or equal to, because of the closed dot, less than or equal to 1. So x is between negative 3 and less than 1, less than or equal to 1. So that's my first domain. So let me just maybe clear some of this. I drew that circle. Let me see if I can redraw it to be open. All right, now for my blue domain, I'm starting here. This is my smallest x value, and that is at x equals 1. And then I'm going all the way until x equals 3. Okay, so x is going to be between 1 and 3. Both get a little line because we have closed dots on both ends. Now what about this green thing? So this green thing, we start at an x value of 3, and we end the green thing at an x value of 5. So x is going to be greater than or equal to 3, but strictly less than 5 because of the open dot right there. And finally, let's do the yellow thing. Oops. So because there's no dot, I'm assuming that this goes on forever. Okay, so the lowest x value I have here is 5. And actually, let me rewrite this real quick. Okay, so the lowest x value I have is 5. So we have x is greater than 5, right? Because it could be 6, it could be 7, it could be 8, 9, 10, but it goes on forever, right? We're assuming that it goes on forever, so we don't need to squish them in between anybody. It's just x is greater than 5. Okay, so let's go ahead and now actually write the line segments down. So this one right here, the first thing you should notice is I have a y-intercept, which is good news. The y-intercept is 5. Now I need to figure out what the slope is. And I think I can just do rise over run pretty easily to figure this out. So the slope is rise over run. So I can pick any 2 points on the line. Any of them. It really doesn't matter. And I want to see what the rise over run looks like. So I'm just going to pick this guy, I'm going to pick this red point right here and this black point. Those are both on the line. So to get from red to black, I'm rising 1, let me do it in green, 1, 2 in the negative direction because I'm going down. So we have rise is -2 over run, I'm going 1 to the right. So that's going to be a positive 1. -2 over positive 1 is going to give me -2. And so my function of that red line, it's going to be y equals m, which is -2x plus 5. So that's my rule that I'm going to write up here. And I don't have to write the y because the y is already there, technically. All right, very nice. Now let's check out the blue one. So I need 2 points on the line. And how about we just choose this one? We don't know what the y-intercept is quite yet. We can probably figure it out pretty easily by just getting the slope. We don't necessarily have to do any kind of plugging in if we don't want to, but if you like doing that, that's fine too. So I'm going to pick these 2 points, and to get from the leftmost point to the rightmost point, I have to rise up 1, 2, 3, 4. So I'm rising up positive 4, and I'm running to the right 1, 2. So that's a positive 2. So positive 4 divided by positive 2 is a positive 2. That's my slope. Now, 2 negatives also make a positive. So if I were to, work backwards to find this, to find out what my y-intercept is, I could certainly do that. I'm going to just show you that right here. I could go down 2, 1, 2, and to the left 1. Right? I went down 2 to the left 1. And this is valid, right? I did the slope. I rose 2, ran 1, but I did it down and left, and so when I do down and left, a negative divided by a negative is a positive, so that's why that works right there. So that's my y-intercept. It looks like it's at positive 1. So b is equal to positive 1. So you could do it like that by just kind of working backwards to find the y-intercept. Or you could do what we did before and choose one of these points, such as this is x equals 1, y equals 3. You could have used x is 1, y is 3, and m is 2. Plug all of this into y equals mx plus b and solve for b, and you would get the same answer. So we found that our slope was positive 2, and we see that our b is positive 1. If this were to keep going. So our formula is going to be y equals 2x plus 1. Okay? All right, let's look at the green little segment here. So the green segment, what is my slope? Well, to get from one point to the next, I'm not rising anything, right? I'm not moving up or down. I'm just kind of staying flat. So my rise over run, since I'm staying flat, I'm not rising, so that's 0. And I'm running 1, 2 to get to the next point. So 0 over 2 is going to give us 0 for our slope of the green. All right, so m is equal to 0, and we can see what the y-intercept is because this is a flat line. It's just gonna extend right to the y-axis just like that, and it's gonna eventually touch it right here, and that happens at 6, 7. That happens at 7. So that is my y-intercept here. Alright, so my equation is y equals 0x plus 7, but the 0x is just 0, so really we can just write 7. 0 times x is 0. Okay, and finally let's do the yellow piece. So let's figure out what the slope is first. So the slope, if I want to go from the topmost point to the bottommost point, I have to rise down 1, 2, 3, 4, 5. So I'm going down 5, and then I'm running 1, 2, 3, 4, 5. So plus 5. And so my slope is going to be negative 5 over positive 5, which is negative 1. Now I need to see what my y-intercept is. So I'm just going to do it the way that we did it before, and I'm going to say, okay, well, this point right here is on the line. It has an x-coordinate of 10, and it has a y-coordinate of 2. So I'm going to use this point along with the slope to plug everything into my equation and solve for b. So my equation is y equals mx plus b. Plug in 2 for y, negative 1 for m, 10 for x, and we're looking for b. So on the right side, I get 2 equals negative 10 plus b. I'll add 10 to both sides to get b equals 12. So my equation for that yellow segment is y equals m, which is negative 1, x plus 12. All right, we did it. So that was kind of a process, but this right here is our formula that represents this piecewise graph. All right, so now let's go the other way. Let's actually graph the piecewise functions. So I'm going to do a rough sketch here, and actually maybe let's see if we can put it on graph paper. That might be better, and maybe I'll rewrite it over here. That's a good idea, Sarah. Okay, so we got 3x plus 1 for x is between 1 and 2, and then we have 2x when x is greater than 2. Okay, let me erase all of this stuff. So the first thing we can do, we can graph this first rule right here. So the rule is y equals 3x plus 1 when x is between 1 and 2. So I like to just plug in my x values to see what the ordered pairs correspond to. So when my endpoints here, so 1 and 2. So here's what I'm going to do. I'm going to say, well, when x is equal to 1, even though we know it technically can't be equal, we still want to get a little open circle somewhere. So when x equals 1, we're just plugging in 1 into my rule up there. 3 times 1 plus 1, and that's going to give us 4. So when x equals 1, y equals 4. So 1, this is 1, 2, 3, 4. And so we have this point right here, but it's going to be an open circle, right? Because we plugged in 1, but technically 1 is undefined on this line. We have a greater than sign. So it's going to be an open circle there. Then I'll plug in the other endpoint, which is 2. This is our other endpoint. So when x is equal to 2, what we have is 3 times 2 plus 1, and that's going to give us 7. So when x is 2, y is 7. 1, 2, 3, 4, 5, 6, 7. So this is 2. And then it's going to be a closed dot because at x equals 2, it's defined, right? X can be less than or equal to 2, but at the same time, greater than 1. So then we just connect the dots, and that's our first line. Okay, let's look at the other one. We have 2x, y equals 2x. So we want to see what happens at x equals 2, because that's really the only point that we have to work with here. I mean, let's see what happens when x is equal to 2. So when x equals 2, we get 2 times 2, right? I'm just plugging in 2 into my function here, which is our output y. So 2 times 2 is 4, so when x is equal to 2, y is equal to 4. So we have 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Okay, there we go. Alright. And so we need 2 points to define a line. So I'm just going to pick another random x value to the right of it, since it's going to be x is strictly greater than 2. So I'm just going to pick 3 to plug in so that I can get another point. So when x is equal to 3, we have y is equal to 2 times 3, right? Just using our function rule. And so y is equal to 6. So our ordered pair is 3, 6. And so that is going to be 1, 2, 3, 4, 5, 6. So it's going to be like this. And then it's going to go through this point, and it's just going to keep going, right? But it's not going to continue on to the left, because this function is only valid, this line is only valid when x is greater than 2. So anything to the left of it can be ignored. On the other hand, 3x plus 1 can be ignored, everything to the left of 1, right? And everything to the right of 2. So that is going to be our piecewise function there. Okay, let's try another one. So this time we have 3 different rules here. Let me go ahead and bring out my coordinate plane. And I'm going to actually just rewrite this down here so that it's a little bit more clear. Okay. Alright, so the first function I have is 2x minus 4. And so, like, I need 2 points to define the line, but the first point I'm going to use is x equals 6, because that's our endpoint there. So when x is equal to 6, we have y is equal to 2 times 6 minus 4, just plugging in 6 into that function. And I get y is 12 minus 4, which is 8. So 6, 8 is a point on this line, and so I'll just plot it. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and actually it should be an open dot because 1, 2, 3, 4, 5, 6, 7, 8. Because of the strictly less than sign. So x is strictly less than 6. So it needs to go in this direction. But I need another x value to connect the dots. So I'm just gonna pick x equals anything to the left of it's gonna work. What about x equals 0? That's to the left of 6, right? Because I'm trying to connect the dots going that way. X is less than 6. So when x is 0, if I plug 0 into my function up here, I get that y is equal to 2 times 0 minus 4. So y is negative 4. So I have 0, negative 4. And that's going to be right here. And so since it's not bounded by anything, this line isn't bounded, we can just kind of connect the dots and draw a line saying that this goes on forever. Okay, so that's our first one. Then we have the next guy is just 1 between 6 and 8. Okay, so if I plug in x equals 6 into this function, there's nowhere to plug it in, right? X can be 6 because there's no input value, right? So when x is equal to 6 in the second function, y is equal to 1. It can't be anything else. It forces us to have 1. Like there's no x to even plug in. So we can go ahead and plot that point. So when x is equal to 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, y is equal to 1. And it's going to be a closed dot because of this less than or equal to sign. In a similar way, when x equals 8, there's no x to plug in here in our rule. Y is automatically going to be 1, and who cares what x is, right? It's just going to be a straight line. So when x is equal to 8, y is also equal to 1, and it's going to be a closed dot. And we're just going to connect these guys in a straight line like that. And finally, we have one more piece to this. We have x minus 1 when x is bigger than or equal to 8. So I'm naturally going to plug in 8 into my function here. So when x is equal to 8, y is going to be, well, plug in 8 for x. 8 minus 1, we get y equals 7 when x is 8. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. And then up, 1, 2, 3, 4, 5, 6, 7. Okay? And that's going to be a closed dot, right? Because we have greater than or equal to. Now, since we have greater than or equal to, we want to connect the dots going to the right. So I need another point on the line, and I can find that by plugging and chugging, or I can use the fact that this thing has a slope of 1 to get my next point. So the slope of 1 is going to tell us this goes up 1 and over 1, and so this is going to be another point on my line here. And so I can connect the dots. I can connect the dots starting at x equals 8 and going forward like that. So just for reference, this guy right here is x equals 6. This guy right here is x equals 6, x equals 8. This guy right here is x equals 8. Okay, so you can kind of see how this picture goes along with our graph here. Okay, so let's try to find the domain and range of a piecewise function. So our pieces, we have this first piece right here and our second piece right here. And what I'm going to do is I'm going to look at Desmos to talk about the domain and the range. If you go to Desmos, and this is how you put in a piecewise function. You put in the first piece on the first row, x to the third, and then in the little curly brackets you put in the domain for that piece. So x is less than 1, and then on the second line is my second piece, 1 over x to the fourth, and in curly brackets I have x is greater than 1. So what's the domain here? Well, the domain is going to be all real numbers because x can be anything we want, right? if x can be 0 as well, you might be thinking, oh, well, what about the 1 over x to the fourth? Like, x being 0, that's a big problem. Well, that piece, x isn't allowed to be 0, because x has to be bigger than 1 for that piece. So the x equals 0 part is covered by the red piece. That's totally valid for the red piece. And we can see that x is all real numbers. If we just examine this graph, kind of look to the left, look to the right, we can see that x can be anything. All right, there's no restrictions there. So for our domain, we have all reals, or all real numbers, negative infinity to positive infinity, if you like that. And for our range, this is how far down to how far up does it go. So how far down does it go? Well, it goes down forever and ever and ever, right? But it stops right here. So this is the highest point that it goes right there, and that is at x equals 1. So that's the highest point. Now, it says it's undefined, but it's not undefined for the red piece, right? Because when x can be less than or equal to 1 for the red piece, and if we plug in 1 for x, we get 1 as our output. So the highest this thing goes is 1, and the lowest it goes is negative infinity. So to say this, in terms of inequality, we can just say that x is less than or equal to 1. Or maybe I should say y. Well, maybe I should say capital F of x, because that's what we're using as our y here. So the range is capital F of x is less than or equal to 1. Why? Because the highest point that it goes is y equals 1, and the lowest point that it goes down forever and ever. So that is our range. Then it says to evaluate f of 0 and f of 2 and f of negative 1. So for 0, remember this is our input. Are we using the first rule or the second rule? Well, we're using the first rule because x is 0 in this case, and that falls in the x is less than or equal to 1 category. So we have to use this rule right here, and we're just going to take our input 0 and cube it. That's what it tells us to do, and we get 0. For f equals 2, this time our x falls in this category. X is bigger than 1. So we plug 2 into this rule right here. We get 1 over 2 to the fourth. So that's just 1 over 16. And what about f of negative 1? Well, negative 1 falls in this category. Negative 1 is less than or equal to 1, so we use this rule right here, and we get negative 1 to the third. Negative 1 times itself 3 times is negative 1. That's our answer. Okay, so let's take a look at this example of a problem where we could use piecewise functions to come up with a formula. So a company produces a new product, and they have a fixed cost of $300 for producing any number of products. The first 2,000 items cost $11 each to produce, and after that, each item costs $4 to produce. So for part A, we want to write a piecewise function to model the situation. We want to call the function f of n, where n is the number of items produced. So we're going to have two separate rules, right? Because we have some constraints here. The first one, it says that, we're going to have some cost for the first 2,000 items, okay? So the first 2,000 items, n, I can represent by n is bigger than or equal to 0, or less than or equal to 2,000, excuse me. So how many items we're talking about is part of our domain, right? Because it's our input here. And the cost is going to be our range. So for this first situation, what kind of function can model this? Well, since they have a fixed cost of $300, we're going to have 300 plus the cost per item. So the cost per item is going to be $11, right? So this is going to be 11 times n. Right, so if we produce 0 items, it's going to be 300 plus 11 times 0, 1 item, 300 plus 11 times 1, etc., etc. And this can go on all the way until 2,000 items. But at 2,000 items, something changes, right? It says after 2,000 items, it costs $11 each to produce. I'm sorry, I read that wrong. After the first 2,000 items, it costs $4 to produce the items, okay? So, the idea here is to first see how much it costs for the first 2,000 items, right? So, for the first 2,000 items, it's going to cost 300 plus 11 times 2,000, right? I'm just plugging in 2,000 for my items. And what I end up getting is 22,300, right? So I'm going to have 22,300 plus something. And this time my domain is going to be anything bigger than 2,000. So n is going to be strictly bigger than 2,000. Okay, so this is the first 2,000 items. And then anything after that is going to cost 4 times the number of items. Now, you might be tempted to put 4n. But remember, the n stands for the number of items in this case. And so it's not going to make any sense, because if we put in 2001, for example, for n, well, we're only adding one more item onto this. We're only adding 4 times 1 onto it. We're not adding 4 times n onto it. So what we need to change this to is not 4n, but 4 times n minus 2,000. And that'll give us the right answer, because, as I said, if n is equal to 2001, if you take 2001 and subtract 2,000, you get 1. 1 times 4 is 4. So the cost of 2001 items is going to be the cost of 2,000 items plus the cost of one more after that, which is $4. Okay? So hopefully that makes sense. I know this is kind of a harder concept to wrap your head around, but really try to think about this example. This is actually a really important example. So there we have it. We have our rule right here. So this is going to be, we have our rule, and then on the right side we have our 2 domains. Okay, so it says explain the domain and range in terms of real world terms. So what we can do is we can just put this in Desmos first. Notice I'm putting X's. Desmos likes our input variable to be X. Okay, I'm going to zoom out a little bit. So that's our first piece, and then we have 22,300 plus 4 times X minus 2,000. And our restricted domain, we have X is greater than 2,000. Okay, so there is our graph here. Okay, so what is the domain? Well, the domain is what can X be. And we can see that our domain starts here when x is 0, and there's really no breaks in the graph at all. There's kind of this curved, like this curved point when the pieces shift, but other than that, if we keep moving up, we can see that this thing goes on forever in the right direction. So our domain, and we're using n here, domain, n can be bigger than or equal to 0, right? Can be anything bigger than or equal to 0. And what does this mean in our context? Well, we can produce 0 or more items. That's what it means. Okay, and what about our range? So our range is how far down to how far up does this thing go. And we can see that the very lowest point that this thing goes is 300, and the highest point it goes is forever and ever, right? So the range is going to be f of n is bigger than or equal to 300. And what does this mean in our context? Well, remember that f of n is the cost, okay? And so what this means is that even if you don't produce any items, you're still going to have to pay that fixed cost of $300. Okay, so even if you don't produce any items, you still have to pay $300. Okay, so what is f of 4,000, and what does it represent in this situation? So 4,000 is going to be our items, right? Because it's our input. So and the output is our cost. So f of 4,000 is going to be the cost of producing 4,000 items. Okay. Now, which rule are we going to use for this? Are we going to use this rule right here, or are we going to use this rule right here for 4,000 items? Well, we're going to use this guy because it says that, when our items exceed 2,000, we want to use this rule right here. All right. So we can figure this out. Let's do f of 4,000. We're going to use our second rule, so we're just plugging in 4,000 in for n. Let's compute this. And we get 30,300. So this is going to be the cost of producing 4,000 items.